Swayam Prabha. Digital India. Educated India.
Good morning, everyone. Welcome to this course of Introduction to Electronics. We have started a new device in the last class, which is BJT, that's bipolar junction transistor. Let's recapitulate what we discussed in the last class. Okay, BJT stands for bipolar junction transistor. Okay, as the device will have both the carriers, electron and holes motion, so it is called bipolar. We have also discussed the structure of BJT. So this is a typically a 3-terminal device. Okay, if you remember, we have emitter, we have base, and we have collector. So these are the 3 terminals. Okay, and there are 2 junctions. One junction is a base emitter junction, and another junction is base collector junction. Okay, so BJT can be it can be made of NPN, okay, or it can be made of PNP. Okay, so so you see, or it can be made of PNP. Okay, so these 3 regions I'm talking about. So you see that the doping of emitter is the highest, then that of base, and then that of collector. This is as far as doping is concerned. Okay, what about the area wise? Area wise, base is the thinnest. Okay, and collector is the largest. Okay, so these things we have discussed in the last class, and also we have mentioned about the symbol of BJT. The symbol is typically like this. Okay, you see, this is your base, this is your emitter, and this is your collector. And the convention is emitter will contain an arrow. Okay, and the direction of the arrow is the direction of the motion of current. Okay, direction of current. So this is typically NPN BJT. Okay, where emitter and collector is N-type semiconductor and base is P-type semiconductor, which is sandwiched between emitter and collector. Okay, what about PNP BJT? The symbol is almost same. The only difference here is the direction of arrow. You see, here also you need to give the arrow in the at the emitter terminal. Okay, and the direction of the arrow is represents direction of the arrow represents the direction of current. Okay, so here in case of PNP transistor, so N base is again sandwiched between emitter and collector, which is made of P-type semiconductor. Okay, and in case of PNP, the current is entering from the emitter side. Okay, whereas in case of NPN, current is coming out from the emitter side. Okay, so this part we have discussed in the last class. We have also started our, we have also mentioned that although this is a there are two junctions, okay. So we mentioned that if it is like if it is like if it is like NP and BJT, okay, then you see in this in the two junctions there will be two back-to-back diode like this, because both are, this is one PN junction and this is another PN junction, okay. Similarly, in case of PNP transistor, okay, um, in case of PNP transistor, there are there are again two diodes. The direction of the diodes are like this, okay. So you see, so you see and we mentioned that even if there are two back-to-back diodes in this at these two junctions, still we can't really get the performance of BJT if we connect two diodes side by side, simply because we mentioned this base region, base width is very tiny, okay. So if you connect two diodes side by side, and then it will not perform as BJT, okay. So this part we have discussed in the last class, and also we mentioned that as there are two junctions, there can be four combinations of your biasing, okay. So this B junction can be forward bias or reverse bias. Similarly, this BC junction, okay, this can be also forward bias and reverse bias, okay. And we mentioned that the primary interest, if we are applying the BJT as an amplifier, that we will discuss in more detail in the next chapter, okay, or as a switch. So if it is an amplifier, then the biasing is like this. B junction should be forward bias, okay, and BC junction should be reverse bias, okay. And if it is a switch, then this B junction is reverse bias, okay, BC junction reverse bias. That is one case when the switch is off, okay, or uh, or B junction forward bias, okay, BC junction also forward bias. This is when switch is on, okay. So these things we will discuss in more detail later on, but I just want to mention whatever we have discussed in a nutshell in our last class. I think we have also pointed out that as there is doping difference in a BJT, okay, there is concentration of dopant is different. So in the emitter it is heavily doped, then it is base, okay, then it is collector, okay. Now if that is the case, if we draw the if we draw the depletion region, I think we have discussed that any PN junction will have depletion region, and depletion region will basically contains immobile ions, that is depleted of carriers, okay, free mobile carriers. So you see these are the depletion region, okay. So these will contain positive immobile ions, this part, okay, of the junction, and this will contain negative immobile ions. But the point I would like to make is with depletion region this side will be less compared to with in the depletion region this side, simply because P is P has lower doping concentration compared to or base has lower doping concentration compared to emitter. What about base and collector junction? Base again will have doping will have immobile ions, in negative immobile ions in the depletion region, because holes have left and leaving behind this negative immobile ions. What about the collector? Collector will have positive immobile ions, okay. But the point I would like to make again, that the depletion width at the collector is the highest, okay, and it is of course more than that of the depletion width present in the base side, okay. So that is thus far we have discussed in the last class. Let's begin where we left. We mentioned we were discussing this particular slide, which basically shows let me, yeah. So this slide we were discussing at the end of the last class, where we tried to convey that what are the current components present in a BJT, okay. Now, so the left hand side is, as I pointed out, this left hand side is NPN transistor or NPN BJT, okay. So this is your emitter, okay. This is the middle green portion is the base, and the blue portion at the right is collector, okay. Now if you look at the biasing, emitter is connected to the negative terminal of the supply voltage, and P base is connected to the positive terminal of the supply voltage. What it means, if this VBE is more than 0.7 volt, if it is silicon, and if this BJT is made on silicon, and if VBE is more than 0.7 volt, then this base emitter junction will be forward bias, okay. Base emitter junction will be forward bias. What about the supply voltage polarity in the base collector junction? You see, positive terminal of the supply voltage is connected to collector, and negative terminal of the supply voltage is connected to base. What it means, this base collector junction, okay, is reverse bias, right? Because positive is connected to the collector and negative is connected to p-type base, right? Now if we look at the carriers which are moving in this particular device on the left hand side, you see majority carriers are electron in emitter. Okay, so electrons, as this B junction is forward bias, electron will be able to cross this junction and come to the base. Okay, that is we have shown with this grayish arrow. Okay, what about the holes present in the base? Holes will be able to cross the junction, B junction, and will come to the emitter. Okay, so that is like this white arrow I am showing. Now, apart from this phenomenon, there will be another thing will happen, which is these electrons which manage to cross this base emitter junction, some of them will interact with the holes present in the base. Okay, and they will recombine. The electrons and holes will recombine. Okay, what about the rest of the electrons? Rest of the electrons which will come closer to this base collector junction will be able to cross this junction. This is because these electrons which are closer to this junction will feel attraction because of this positive terminal of the battery. Okay, and they will be basically drifted to collector, right? Let me reiterate once more, the electrons which manage to cross this base emitter junction, most of them will be able to reach the collector. The reason behind that, the doping concentration of base is lower compared to that of emitter, and also the width of this base is much narrower, so that electrons will not get enough opportunity to recombine with holes. So most of the electrons which are present, which will come to the base, will manage to reach the collector, right? Now we can mention, we can articulate different currents. Okay, so as electrons are moving from left to right, okay, let's look at the base emitter junction again. As electrons moving from left to right, they generates a current which is in the direction opposite to the motion of electron. Okay, and I have designated that as IEN, right? What about the movement of holes? Holes, those manage to cross the junction, base emitter junction, will give rise to a current which is in the direction of the hole. Okay, movement of hole. So you see, that is I have designated as IEP. So IEN and IEP, both of them, both these currents are in the same direction, and these two, if you add, it is basically the total current is IE, that is the current which is coming out from the emitter. Okay. The base current, there are two components. One is I have represented as IB1 and another is IB2. Let's talk about IB1 first. IB1 is because of the forward biasing of the base emitter junction. So holes manage to cross this junction and gives rise to a current. So those holes will be replenished by from here, from the base terminal. Okay, from this supply. So these holes give a movement of holes from base to emitter, demands more holes coming from the supply voltage. Okay, so that gives rise to a current which is basically IB1. What about IB2? IB2 is because there is recombination. I mentioned few electrons will recombine with few, and that holes you need to replenish from this supply voltage again. So that gives rise to a current IB2. So there are two components of current at the base. One is IB1 because holes manage to cross this base emitter junction, and another is IB2 because holes will recombine. Some holes will recombine with some electrons, few electrons, and give rise to a current which is basically IB2, because you need to replenish those holes from the power supply. Okay. What about the collector current? As electrons manage to come to the collector, there will be collector current, and direction of the current is obviously opposite to the motion of the electron, which is this. So you see collector current plus base current give rise to emitter current, because base current is entering, collector current is entering to the device, whereas emitter current is leaving the device. Okay, so if I use KCL, it is Kirchhoff's current law. It is basically IE, we can say IE equal to IC plus IB. Okay, this discussion is equally valid for the picture I have depicted on the right hand side of the slide. Here you see this is a PNP transistor, whereas the left one I mentioned is NPN transistor. In case of PNP transistor, you see this is emitter, this is base, and this is collector. So I have biased this base emitter junction in such a way that positive terminal of the battery is connected to emitter, that is p type semiconductor, and negative terminal is connected to the n type base. So you see, if VEB is more than 0.7 volt, then this junction, base emitter junction, will be forward bias. Okay, if it is more than 0.7 volt. What about the base collector junction? Base collector junction, this negative terminal of the battery is connected to collector, that is the P, and positive terminal of the battery is connected to base, that is N. So you see this particular junction is reverse bias, right? Now if we then look into the components of current, the similar discussion which I have gone through in the for the left hand figure is equally valid for the right hand one. However, in this case, you see, as base emitter junction is forward bias, holes from emitter will be able to cross this junction. Okay, base emitter junction. Out of these holes, some hole, very few, will combine with electrons present in the base, because base majority carrier is electron, whereas hole is the majority carrier in the emitter, because it is a p type emitter. Okay, and rest of the holes, what will happen to them? They will manage to go to the collector. Okay, simply because this negative terminal of the supply voltage will drag those holes so that they will reach the collector. Okay, so if we look at the current in the emitter side, there is current because of the movement of the hole from emitter to base, that is IEP. Okay, some electrons will be able to cross the junction. Okay, this is the white arrow I am showing, because this junction is forward bias, and because of this movement of electron, there is direction of current which is opposite to that of the movement of electron. So this IEP and IEN is in the same direction, and the effective direction of the current is from the emitter side, as if the current is entering. Okay, again in the base there are two components of current, like I have already mentioned. One is IB1, that is like because electrons are able to cross the junction, base emitter junction, and another is IB2, because some electrons manage to recombine with the holes which entered from the emitter side. So this IB1 and IB2, because of IB1 and IB2, I mean because of these two phenomena, there will be less number of electron in the base, and you need to freshly supply electron from this base terminal. Okay, so that the electron will be compensate, number of electron will be compensate or replenish. Okay, so this gives rise to current IB, which is basically direction of current is opposite to the motion of electron, that is base current is leaving the base terminal. Okay, or coming out of the base terminal. And the collector holes are reaching to the collector, so collector current is in the direction of the motion of the holes. Okay, so here also you see IE current is entering, and from the emitter terminal current is entering, and from base and collector the current is leaving out of the device. So we can again write here also IE is equal to IC plus IB, right? So in now the point to be noted here, base emitter junction is forward bias and base collector junction is reverse bias. That is one point. Another point is depending on whether NPN or PNP, okay, if you referring NPN, we usually saying like VBE, VCB, okay. Whereas if we are referring PNP, we are mentioning VEB and VBC. The way this nomenclature is, you see the terminal is connected to base here on the left hand side, okay. So this B comes first, okay, whereas this negative terminal is connected to emitter, so E comes later. So VBE, VCB, the collector, a positive terminal is connected to collector, so collector C comes first, then B, okay. So the point to be noted, the voltage subscript switched. If we, so here you see VEB instead of VBE, okay. So these are just convention. Here also I am saying VBC instead of VCB here. So you remember that for PNP and NPN you need to switch the subscripts, okay, of the voltages, and the current direction will be reversed. In case of NPN, you remember in case of NPN, current is coming out from the emitter side, whereas in case of PNP, current is going in, okay, current is going in here in the emitter, right. So so current direction will be reversed, okay. So this part I have I think I have started discussing in the last class. Now so this is if we go even further and discuss thing in little bit more detail as per the and try to formulate mathematical equations out of those current, you see as base emitter junction is forward bias, the emitter current is obviously is proportional to exponential VBE over VT. That is from the diode discussion we can appreciate that, okay, because base emitter junction is forward bias, so the emitter current will be exponential VBE over VT proportional to, right. What about the base current? We mentioned there are two components of base current. One is IB1 because the carrier may be able to cross the junction because base emitter junction is forward bias, and another current is IB2 because there is a little bit of recombination at the base between the two types of carrier, electron and holes. Now you see in these both these components is proportional to exponential VBE over VT. Why? Because this first component depends on obviously how forward bias it is, okay, and second forward bias is the junction, and of course the second component also depends on exponential VB over VT because the more the number of carriers, more will be the recombination, right, and the number of carriers depends on exponential VB, that is a biasing, exponential VB over VT. So we can write this that total base current is proportional to exponential VB over VT. What about the collector current? You see collector current also depends on the base emitter voltage, okay. Why? Because collector current will basically will depends on how many carriers manage to come to the base from the emitter, right, because almost that number of electrons or almost that of holes will be able to cross the junction, okay. So in other words, the number of carriers reaching the collector depends on this base emitter junction voltage. It doesn't depends on the collector base junction voltage, okay. So we can again write that this collector current also depends on exponential VB over VT, but it is independent of base collector voltage, right. The point to be noted that base current will be much smaller than emitter or collector current because base doping is less and base width is less, okay. What about the collector? Very close to that of the emitter current, simply because most of the carriers which is coming to the base will be able to reach the collector, okay, because very few of them will recombine. You see, very few of them will recombine because the base width is less, right? So most of the carriers which manage to come to the base will be able to reach the collector if proper reverse bias is given in the base collector side, right? Now let's move, and so we have I think come across this equation in the last class. So we can write IE equal to IB plus IC, that I know, that I already discussed to you, and beta is beta I am writing as a collector, and collector current and base current both are both are linearly related, because both depends on the exponent, both are exponential function of base emitter voltage. So we can write them as IC over IB with a term which is called beta. Okay, this is known as current gain. Okay, common emitter current gain. Beta is known as common emitter current gain. Usually the value of beta is a few hundreds. Okay, what about the uh, what about the collector, relation between collector current and emitter current? We mentioned that collector current and emitter current very close to each other, rather collector current is little bit less than that of the emitter current, because some of the carrier is managed to recombine at the base. Okay, and this is usually represents as IC is equal to alpha IE, where alpha is very close, slightly less than 1. Okay, usually somewhere between 0.9 and 0.99 say. Okay, so it is close to 1, but it is less than 1. Okay, because some carriers will recombine at the base. So these things I have, I think very quickly I have mentioned in the last class. Now let's move and discuss IV characteristics of BJT. Okay, let's start with common base configuration. What is common base configuration? Common base configuration is where base is grounded. So this is my base terminal, base is grounded, and base is base is common between input and output. Okay, sort of this is your output terminal. Okay, and this is your input terminal here. So base is between input and output. Okay, and so base is common, base is in common between input and output, and base is grounded. So that is why this configuration is known as common base configuration. Now if you look at the biasing again, you see this positive terminal of the VBB is connected to, this is an NPN BJT. Okay, because you see from the emitter current is coming out, so this is an NPN BJT. So you see positive terminal of the battery is connected to P type base, and negative terminal of the battery is connected to N type emitter. So if we give proper VBB, then this particular junction, base emitter junction, will be forward bias. By forward bias I mean this particular junction will have at least 0.7 volt. Okay, what about the junction, base collector junction? You see this positive terminal of the battery of VCC is connected to the collector, which is N type, and negative terminal of the battery is connected to base, which is P type. So this is like reverse bias. Okay, this base collector junction is reverse bias. Now getting to the detail of the characteristics, let's look at the input characteristics. Input characteristics is here there are two variables. One is input current, okay, that is IE, that is emitter current, and the other variable is base emitter voltage, VBE. Okay, now if you plot IE versus VBE, this is the current will vary exponentially, because we know for any forward bias PN junction the current is exponential, proportional to exponential VBE over VT. So current is varying, you see, exponentially, right? Now there are 2 points I would like to mention. This if you take a slope here, okay, if you take a slope, then your then you will get a resistance which is known as dynamic input resistance, that is delta VBE over delta IE. Okay, if you take a slope here. Now I have also shown that the collector base voltage VCB, so VCB2, VCB1, so I have plotted these input characteristics for two collector base voltages. So you see, if we increase collector base voltage, your emitter current is going to increase. Okay, your emitter current is going to increase. The reason behind, if you increase your collector base voltage, your let me draw it. Okay, so this is your base, this is your emitter, this is your collector. Okay, so if you increase your collector base voltage, what will happen? This base collector junction will be more reverse bias. Okay, if we increase this, because base collector junction is reverse bias, if we increase this voltage, okay, the collector base junction will be more reverse bias. Okay, now if collector base junction is more reverse bias, that means the depletion region present here is going to increase even further, both in both direction, both in the base side and also in the collector side, right? Now if this depletion region increases, because we are increasing the this reverse bias voltage, what it means, the effective base width will decrease. Okay, let me zoom it bit further. So what I am trying to show here, that let me choose another color again. So say this is my base. Okay, this is my base. Now I have so if I have now this is the depletion region because of VCB1. Okay, and if you increase the collector base voltage, the depletion region will increase further, will go inside the base, right? That is also, the depletion region will increase in the collector side also, but let's concentrate only on the only for the depletion region in the base. Now depletion region this side, there are also a depletion region which primarily depends on the base emitter voltage of the applied base emitter voltage. Now you see, this increase in the depletion region will effectively will reduce the effective base width. Okay, will reduce this effective base width. So this is the newer base width. The earlier base width is up to this. So if effective base width decreases, then less number of carrier combine at the base. Okay, and if less number of carrier recombines, in this case it is an NPN transistor, so electrons are moving, sorry, so electrons are moving from emitter to collector. Okay, that gives rise to current. So less number of electrons will recombine, so that gives rise to a more emitter, more larger amount of IE. Okay, because less number of electron will be able to recombine now, so that gives rise to, so that is why you see, for the same base emitter voltage, now you have more current, more IE compared to what is here. Okay, so if you increase your collector base voltage, your emitter current is going to increase. So there are two parts of it. Let me reiterate again. So one is this emitter IE is exponentially proportional to exponential VBE over VT. Okay, that we have already discussed, because this is a PN forward bias PN junction. That is one thing I would like to mention again. And other thing is this dynamic input resistance, and also this emitter current will increase if we increase the collector base voltage. Okay, so that is the input characteristics part. What about the output characteristics? Output characteristic is looks like this. Here we are plotting IC, that is the collector current, okay, versus VCB. So these are two variables at the output side, collector current and collector base voltage, okay, VCB here. And these I am plotting for different values of IE, okay, different values of emitter current. Now you see, as we increase IE, IC is also going to increase, and value of IE and IC is very close because alpha is close to 1. Okay, it is little bit less. Now there are three regions in this particular characteristic. One is active region, one is saturation region, and one is cutoff region. Okay. Now this active region is the region where let me clean this because it becomes too clumsy. So active region is basically the region where you have your where your base emitter junction is forward bias, you remember, and base collector junction is reverse bias. Okay, so let me so let me repeat it once more. So base emitter junction in the case of active region, base emitter junction is so this is active region, saturation region, and cutoff region. In case of active region, base emitter junction will be forward bias, okay, and base collector junction will be reverse bias. This is for active region. Okay, so that is the region I have just arrowed it here. So this entire region is basically your active region. Okay, what about saturation region? In the saturation region, both base emitter and base collector is forward bias. Both are forward bias. This is saturation. What about cutoff region? Cutoff region is this part. Okay, I have shown it here. In the cutoff region, base emitter and base collector all are reverse bias, or you can say base emitter is less than 0.7 volt. Okay, so there is hardly any current. So that's basically cutoff, right? Now couple of points I would like to mention again, that is you see the collector current is independent of collector base voltage. Okay, that I mentioned to you already, because the collector current depends on the emitter current, right? The number of carriers which is basically crossing the junction will be able to reach the collector, right? So this region, in the active region, the collector current is independent of collector base voltage. It really depends on how many carrier manage to cross the base emitter junction and ultimately to the base collector junction. So if you increase I, IC will increase. In other words, collector current depends on VBE rather than VCB. Okay. I would like to give you another insight. You see, this is a reverse bias. This collector base junction is in reverse bias, right? So if I plot characteristics, okay, I think these I have mentioned briefly in the last class as well. So this is my reverse characteristics of the diode, where this is the reverse leakage current. Okay, we usually designate as IS, reverse leakage current. Okay, and this is your diode current, that is collector base current versus collector base voltage. Okay, and when it is forward bias, this diode will give that exponential rise, but we are not using, in the active region we are not using the forward bias, we are using the reverse bias of the collector base junction. Now this is one current, okay, which is very tiny. I think in the of the order of nanoamp to picoamp, even in of the order of femtoamp, because this depends on minority carrier. You see, so I have, this is my base and this is my collector. So here, if it is a p type and this is n type, minority carriers are electrons. Okay, very few electrons are present because base is lowly doped, you see, and there are also very few holes here because those are minority carriers. And if you connect them as reverse bias, okay, so negative terminal to P and positive terminal to N, so hardly any current, that is the reverse leakage current. You remember, this is we extensively discussed in case of our diode discussion. Now what happened if we somehow manage to increase the number of electrons here? Okay, if we manage to increase the number of electrons somehow, so we have lots of electrons. So if there is lots of electrons, huge number of electrons, then what will happen? This positive terminal of the battery will drag those electrons here. Okay, so all of a sudden you get lots of current, right? So that current is like the current here. Okay, say for concentration N1, I increase the number of electron even further, the current will increase even further. Okay, I increase the current number of electron even further, the current will increase even further. Okay, so you see these currents, okay, which is much more than that of IS, but the property remains the same. This current doesn't depends on the reverse bias voltage I have applied. Okay, now if you just relate this, if you just relate this characteristic with this, I have just swap it. Okay, so you see these currents is nothing but these individual currents, because how we are generating more number of electrons at the base, because we have forward bias this emitter and base junction, so lots of electrons enter from the emitter side if it is an NPN BJT. Okay, so those electrons will see this reverse bias or positive terminal of the battery which is connected to the collector, and they will be drifted to the collector, they will be dragged to the collector. Okay, so we will have, certainly we will have current, and this current, the amount of current depends on how many electrons are present at the base or manage to cross the base collector junction. Okay, so in a nutshell, the more the number of electrons, that is more the IE, okay, more will be your IC, right? And this current, which is basically the reverse bias diode current, doesn't depends on obviously the reverse bias you are applying, right? So IC is independent of VCB. It only depends on IE. The larger the IE, the larger will be the IC, right? I think this part is now clear to you, the active region. What about the cutoff region? Cutoff region is basically when you have this base emitter voltage less than 0.7 volt. If it is less than 0.7 volt, then your supply of electron will be ceased. Okay, so there will be no supply of electron. If there will be no supply of electron, this this IC will be close to 0, or IC will be your IS. You remember, that is the reverse saturation current. Okay, so this cutoff region is here. Even if the collector base junction is in reverse bias, but there is no supply of electron from the emitter side, because base emitter junction is no longer forward bias. In that case, you will have the cutoff region, that is very little amount of current of the order of picoamp to femtoamp. Okay, that is basically cutoff region. So now I think active region and cutoff region is clear. What about the saturation region? Saturation region is the region where both this base emitter and base collector junction is forward bias. So if base emitter junction is forward bias, we will have lots of electron entering to the base. Now if you make this base collector junction forward bias, okay, if you make this base collector junction forward bias, then what will happen? If you make this forward bias, then these electrons you see which comes from the emitter side will not go to collector, because they will see this as a forward bias. Base emitter junction, base collector junction is also forward bias. So it will now follow these characteristics. So what will happen? The current here will go this way, right? So I have plotted this here, you see. So whatever the IC will decrease and goes to 0, okay, because it is now going to forward bias. It is now becomes forward bias, so it will exponentially increase. So IC will go to 0, and then if you increase the base emitter base collector junction even more forward bias, then this will be a diode current, you see, exponential diode current. So I hope it is clear to you. So this is your saturation region where both base emitter and base collector junction is forward bias. In the cutoff region, base collector junction is reverse bias, but base emitter junction is less than 0.7 volt. And what about the active region, which is very important for us, because we will see in the active region we need amplifier. For amplifier application we need to keep this BJT in the active region, and in case of active region, base emitter junction is forward bias and base collector junction is reverse bias. Okay, so this is whatever I have mentioned. This is the slides basically is telling that. Okay, this is your IE and input characteristics. Is emitter current is related with VBE exponentially. Okay, so those things I have mentioned, input characteristics, and also I have mentioned output characteristics. And this output characteristics is basically between IC and VCB, and we have plotted for different values of IE, as I said. And there are three regions: active region, saturation region, and cutoff region. And in the active region, IC is equal to alpha E, where alpha is very close to that of 1 but less than 1, because some carrier will recombine at the base, and IC does not depend on VCB. Okay, this IC is almost independent of VCB. That shows that this can be used a constant current source. In case of constant current source, current of a device remains constant even if you are changing the voltage. Okay, I have a load voltage here. Even if you changing the load voltage, okay, the current through the device remains constant. So that is what is happening. Your VCB will remain the same constant even if your current is varying. You see, current is varying, but your VCB, even if your current is changing, okay, current is changing, but your VCB remains, your VCB will remain the constant. Okay, your VCB will not change, but your current will change. So if that is the case, we can say that sorry, I didn't I think I am telling the wrong thing. So what I am saying, as the current this IC is independent of VCB, okay. So you see, this can be used as a constant current source, because you see, even if you are changing, even if your VCB is changing, here your VCB is changing, but your current is remain the same. Okay, so that's basically a constant current source where your current, so for a particular value of IC, even if your VCB is changing, your current is remains the same. Okay, so that means it can be used as a constant current source. So in a constant current source, if you are changing your load, what happens is your voltage is changing, right, across the load. But if you can maintain the constant, if you can maintain the current through the load, that means it is a constant current source. Okay, so it can be used as a, the output characteristic shows BJT can be used as a constant current source. Okay, and in case of saturation region, you see the linear relationship between IC and IE no longer valid, because IC will quickly drops to 0. Okay, because both these junction now forward bias. And in case of cutoff region, this base emitter is reverse bias, and base collector base is also reverse bias. Here IC is almost equal to 0. So IC is equal to basically the reverse saturation current, because there is no supply of carriers from the emitter side, right? So so today we'll stop here. We have mostly discussed the BJT characteristic, and also we have concentrated today on common base configuration. Okay, in the next class we will cover the common emitter configuration. Okay, in case of common emitter configuration, you will see that the emitter is in between the input and output. Okay, and also emitter is grounded. That is basically common emitter configuration. So that we will cover in the next class. So thank you very much for your attention. Bye for now.